Hello, in this video we'll get into section 9a. So last week we mentioned a few of these ideas just to try and give you a little bit of a sneak peek of where we're going, but today we'll really get our hands dirty, start to see some of the specific problems. This is slightly similar to our previous unit in that 2a we discussed basics of units, and that allowed us to move into 2b, actually solving some slightly deeper problems by using those units. The similarity is in 9a, we get a nice general introduction to what we call functions. Functions are a very, very deep topic. They are often used to create this idea of a mathematical model. This idea of a representation of some situation that helps us to either make decisions or make predictions. That's the idea of what we're hoping to accomplish. But 9a is a little light. We'll get some basic introduction, there's some terminology, there's a little bit of notation, there's a few items we have to practice, but then in 9b, we'll look very specifically at what we call linear models, and that'll allow us to do more work, to get a little bit deeper, to see some more specific examples. So once again, we're building, but this is also a short section. It's just these two sections, and this will lead to a take-home exam, and that'll be our last test. I'll mention more of this in class. We're actually going to use test 3. That take-home is also going to be considered a component of your final exam, but we'll talk more about that in person. But just for you to realize that 9a and 9b, those are going to be the sections for our next test. So, the idea, like they say, they've got some nice little explanation to read through very quickly here. But the idea of a mathematical model, similar to that of an architectural model or a roadmap, gives us something real and helps us to understand the situation a little bit deeper. Now, what we are going to use to make these models is what we call a function. Now, we're not getting, like I said, there's some terminology here, but we're not getting super deep with the definitions. In other math classes, we take this further. What is a function? The whole idea of a function is a relationship between two quantities where we can see how one quantity affects the other. That's the idea here, and even more so, the idea of a function is about an input-output, that we can clearly see that as you input one of those quantities, that leads to the other one, which we consider the output. But like I said, we're not going quite that deep. They give us a few quick examples of some mathematical models, but now we're very quickly starting to jump into the language and the notation. If we're going to talk about a function, we keep suggesting that there are two variables, there are two quantities that we are trying to connect in some way. And when we look at those two variables, we could separate them into the dependent and independent variable. For notation, technically a variable, a letter used in place of a number, but there's a lot of convention that we have already established. So the idea between a dependent and independent is the independent variable kind of goes on its own, but the way that you use this variable will impact this one. So one of the most easy, quick examples I like to discuss is how long did you study for a test, and then what is the grade that you got on that test? The grade you got depends upon how much time that you actually spent studying. So that's the relationship that we look for. That there's always, when we see the two variables, we try and think which one relies on the other, which one connects to the other, and which one kind of goes on its own. So the reason we get two variables here, most of us are used to the XY relationship, and we'll talk a little bit more about that. Sometimes we use variable t standing for time, but I'm a little more accustomed to using an x. So they give us a little bit of that discussion here, and even down here, they start to give us another example. We are looking at a table of values that gives us the time of the day and then the corresponding temperature at that time. So in any situation, time flows no matter what. The temperature of the day depends upon what time it is. And right, if we think about this, as the sun comes up, the day typically gets warmer, and then after the sun starts to set, the day gets cooler, so we can notice how that temperature depends upon the time of day. So that's, again, that's the relationship. That's the situation that we're trying to establish. So as we go to our next page, they try and give us a little bit of practice identifying those variables. So I'm actually going to pop my book open. I didn't make a photocopy of this page, but just to point out at the very, very beginning of this chapter, they pointed out several relationships. Now let's just take an extra moment looking at them and try and figure out that independent-dependent variable relationship. Of course, there is a little catch. So this is the page 512 that they're referring to. And down here, these are those situations. Try and angle so you could see them all. So they have 5 situations here that they just quickly describe. And the whole idea of mathematical modeling, again, they're explaining this before we even got started, we're trying to identify a relationship, how one variable changes with respect to another. We can make these relationships in words as well as equations. We could also see them through charts, through graphs. But that's, again, we're connecting these 2 different quantities, these 2 different variables in some way. And they present several of them here. Now, they restate the statement here. They're missing one because they point out that C, there was no relationship. If we go back to C, the list shown on your receipt for prices of items you purchased at the grocery store, there's just no connection. But if we look at these other situations, the total distance a car has traveled after various amounts of time during a trip, yeah, we could see a relationship there. That the distance you travel depends upon the time that you are traveling. The longer you are in the car, the longer you are traveling, the further you will have traveled. So we can see there is a connection here. And once again, time is once again that independent variable, and the distance we actually traveled would be the dependent. Next, they talk about the way the price of a tablet affects the number of people who buy it. So maybe this is some sort of maybe not a medication exactly, but like some sort of a supplement. There's a hot new supplement at GNC that people like. Well, the price is going to have some effect on who buys it. The dependent variable is the number of people. The price is set, but once that price is set, a cheaper price would probably entice more people to buy it. A more expensive price would probably have fewer people that end up buying it. So price is independent, and then the number of people who purchase would be considered dependent. Our next one, the effect of income tax rates on government revenue. Well, another situation, government revenue and income tax rate. The higher the income tax rate, the more revenue the government would actually have. So the independent variable is the income tax. The dependent is the revenue. The amount of revenue the government collects, the amount of money that they collect from taxes, depends upon the actual tax rate that is being implemented. So that's not always easy though. We're trying to pick some situations that we have a little experience so we can naturally think about how one variable affects the other. But like I said, with C, the list shown on your receipt for the prices of items you purchased at the store, there's just no connection between the items on the list and their prices. They're just 2 completely separate things. So we can't always connect them. And even if we can connect them, it's not always clear which is independent, which is dependent. This is actually a little similar if you go back and we talked about correlation back in our statistics section. And we talked about things like height and weight. We can determine there is a correlation between these two, and we even talked about the nature that typically the taller you are, the more you would weigh. That gave us a positive correlation between these two. But in this same situation, there's a connection here, but which is the independent, which is the dependent? It's not obvious, not at all. Is it the amount you weigh depends upon how tall you are? Or how tall you are depends upon your weight? There's a connection here, but it's not a given that one directly leads to the other. So that's where, like I said, it's not so simple. We read through some statements, it's like, okay, we could figure this out, but we have to be given good examples that we already have some experience with so we can figure this out. And I want to be clear, I would never try and trip you up by giving you a situation that there is no connection or we can't determine it. It would be something like this that we should be able to naturally think our way through. So now the functions themselves. Well, again, we keep showing it. Now we've got XY pairs. And here's the funny thing. Now, even if we go backwards a second, if we are given data in a table, the traditional convention is to give them in that order, X followed by Y. So here, we've got that set up. And like we saw earlier, that same example we keep going back to, this table 9.1 with time and temp, we already decided time is the independent, temperature is the dependent. So they set that up. We could think of that as X and Y, or we could literally describe the two quantities. So time and temperature. Up here, time and distance traveled. Up here, where was it? The price and then the number of people. Over here, the income tax and then the government revenue. So we could literally describe that relationship, not just using generic X and Y, but setting that at that XY setup, but describing the quantities themselves. The function notation, again, there we get more of it, independent followed by dependent. One more time, there's our X then Y setup. Now, our book mentions the function notation here. They don't get too deep. We definitely need to understand the relationship of an XY pair. We're going to have to graph and do some practice graphing and using that in just a few minutes. That's going to be some of the biggest work that we do in this section. But just a little bit more on notation, a few more terms, and then we could really start to see the types of problems that we're going to approach in this first section. So the first thing, writing a function, well, once we have that situation established, which is independent, which is dependent, well, we can get this y equals f of x, but we could be more particular to each situation. So here in example 2, they're talking about as the balloon rises, the surrounding atmospheric pressure decreases. So there's a relationship. As the balloon rises, how high you are above the ground, you get a change in the atmospheric pressure. So therefore, the pressure depends upon your altitude. So pressure is the dependent, altitude is the independent. You're rising, the altitude changes on its own, but then the pressure change depends upon that altitude, how high you are above the ground. So here, just to point out, instead of always using the generic y equals f of x, we can use letters to try and represent the quantities we're expressing. So as an xy pair, we could write it as altitude comma pressure, so that pressure is a function of altitude. Similar, look at the second one here. You're on a barge heading south down the Mississippi River. You notice the width of the river changes as you travel down southward with the current. So the river width depends upon your distance from the river source. The further south you go, the more wide the river is. So width is the dependent variable. Distance from the source, from the beginning, would be your independent. So there's our XY setup. Distance from our starting point, comma, river width. Therefore, the width of the river is a function of the distance we are from the source. So like I said, I'm not trying to go crazy with notation, but we're just trying to be able to see this notation, see this XY setup, and being able to express that in terms of words. So let's go backwards for a minute. Let's already do 2 more over on the side here, and let's think of some common situations. You're out at the store, and let's just keep this simple. You're only buying one item. Let's even make it more simple. You're buying movie tickets. So we're going to have 2 things that we're looking at here. The number of movie tickets and the amount of money spent. The cost would be another way to think of that. What's the relationship here? Is it, do we spend money and that depends on the number of movie tickets we get, or we buy a number of movie tickets and how much money we spend depends upon the number of movie tickets we buy? There it is. We would have this is the independent variable. We just buy our movie tickets, but then how much money we actually spend, our cost, depends on the number of tickets. So as a independent-dependent situation, we would have number of tickets, cost. That could be cost is a function based on the number of tickets. Okay, let's do another one we've already mentioned. We talked about your test grade and the amount of time studied. And we've already established this relationship. Time, again, time is always an easy one. Time is my independent variable. My test grade depends on how many, my test grade depends on how much time I studied. So I've got time and grade. My grade on my test is a function of how much time I studied. So now moving forward, again, just establishing some notation. Now we get to some more terms. But before we get to these terms, I skip page 519. 519 in the book starts explaining some reminders of graphing. So I thought we'd do that a little bit on our own. Certainly more examples in the book, good to practice, but just a reminder of how we graph. That if we have an XY pair, that our XY pair can always be plotted on an XY axis. How we set this up, we have my origin where the two axes meet, and I always represent my points on my graph by first their x coordinate, which would measure how far left or right we go from the origin. If we go to the left, these would be negative values. If we go to the right, that would be positive. And then for the y-axis, we have similar. My y represents how far up, down. Which one is positive, which one is negative. We'd have down would have the aspect of negative, and up would be positive. So let's just take a moment. Let's practice. Let's plot the following points. We'll do a few. We'll do number 1. We'll go 2, 5. Number 2, we'll go 5, 2. Number 3, we'll go -1, 3. Number 4, we'll go -2, -1. Number 5, 0, -2. So if we are going to plot our points, again, I'm going to start fresh, a new XY axis. This is just quick sketching, everybody. I know some people, if you have graphing paper, that's great. It makes this a little bit easier, but you could do exactly what I'm going to do. We're just going to set a scale. We've made lots of sketches before, so we've done, making graphs and charts. We're just, we've talked about making scales, just being consistent. Well, in this kind of setup, let's just make each dash represents one unit. So 1, 2, 3, 4. I'm going 5 units to the right. 1, 2, 3, 4, 5 to the left. There's nothing special about 5. I'm just trying to give myself enough room so I could cover any value here. So again, I'll keep it simple. I'll just go 5 by 5. Up 5 and down 5. Some people still want to get very labeling here. So this is positive 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5, positive 1, positive 2, positive 3, positive 4, positive 5, and negative 1, negative 2, negative 3, negative 4, negative 5. You know, if you need to do that, that's fine. But hopefully we don't have to do that. We'll just make our dashes and do any necessary counting along the way. Oh, one other quick thing I should mention. You notice I don't need a straight edge here. Again, I'm just doing my best. This line, maybe it's got a little bit of a wave to it, so let me just try and thicken it so it looks a little bit straighter. But that's fine. If you accidentally drew your line like that, well, you know, maybe we try and reset. We realize that's way too tilted, so we'd either erase and fix it, or if you're using pen like I am, just draw a fresh one. So we have a nice, relatively straight left-right line for my x-axis and a straight up-down line for my y-axis. So plotting my points, I do x followed by y. X is positive 2, so I go 1, 2 units to the right. But now from here, I don't reset and go back to the origin. From here, I now do the y-coordinate, which says positive 5, so I go up 5 from here. This is where if you have graph paper, all the lines, you've got the whole grid section. But we could just follow, right? I'm here. I'm going to go up 1, 2, 3, 4, and 5. So I can see that point lines up with this dash, and that is 2, 5. In another moment, we'll do this in reverse. First, I want us to just practice plotting the points. In another moment, I'll give you a graph with a few points. We'll make sure we can identify them correctly. The second one, 5, 2, I wanted to do one where it looks like, you know, hey, these look very similar but very different. Same numerical values, but different order. Here, x was 2, y was 5. Now x is 5, y is 2. That makes a very, very big difference. This one, 1, 2, 3, 4, 5 to the right, because positive 5 here. And then I go up 2. So very, very different points. It's not just about doing 2 and 5. You got to make sure you're doing them in the right order on the right axis. Now, number 3 introduces a negative. Well, it's in the x-coordinate. Just means I'm going to go left 1 unit, but then y is positive 3, so I'll go up 3. And that would be negative 1, 3. Now both x and y are negative. Okay. I mean, if you keep going deeper in algebra, people talk about the different quadrants here. These lines break this plane into 4 separate quadrants. Properties that both x and y are positive. X is negative, but y is positive. You know, that's great, everybody, but just as long as we can literally do this, and in just 2 more moments, when we come back to the real problems, this is generic graphing practice. When we come back to the real problems, we're going to see a very nice little bonus touch in just a few minutes. So let's keep going with the generic work. Now we're looking at number 4, negative 2, negative 1, negative 2, 2 units to the left, negative 1. From here, I'm going down 1. So that point would represent this xy pair. And last, this one feels a little weird. X is 0. Remember, we always start here, and then I go left or right as appropriate. But this time, 0. I don't go anywhere. I don't go right or left. I stay here, but then I still have to go down 2, and I would get this point to go with this xy pair. All right, but like I said, we should be able to do this in reverse. We had the xy points. We could plot them in reverse. Here's a graph, and now I'm just going to give you points. We're going to make this is point A. This, let's go over here. This is point B. We'll do this one as point C, and this one as point D. And my directions say, give the coordinates. A, B, C, and D. Okay, so how do we do this? It's kind of the same thing we were doing here. Here we had the xy pairs, start from the origin, do what this tells you, get the point. Now the similarity is we still start here, but now we just literally start counting. If I want to get to A, how do I start here and get to here? Well, first I have to go right. And how far am I going right? I'm going 1, 2, 3 units right. And then from here, I'm going up. How far up? 1, 2 units up. So A corresponds to the xy pair 3, 2. Let's keep doing that. Now we're looking over here at B. Well, the first thing I have to do with B is I need to go left. I'm going left 3 units. So that would be an x coordinate of -3. But then I go up 2 units. So now I get -3, +2. For C, still starting here, I went left 2 units. So that's a -2 for x. But then I didn't go up or down. I stayed right here. So I did not go up or down. That's a move of 0 units on the y side. So we get -2, 0. And last, looking at D, I want to say very quickly, going back to A, let's just use the first example. You should do x first. It's always x followed by y. So in any situation, plotting the points, technically you could have done the y first. Up 5 and then right 2. And then similar here, when I found the coordinates of A, I could have started off by saying I went up 2 and then I went right 3. But I promise you, if you do that, it's almost a guarantee you're going to start flipping your values. So in our format, in our notation, x always comes before y. So if we're given a point, let's keep that habit. Deal with x before you deal with y. And if you're trying to find a point, same idea. Think about the x coordinate before you do the y. So thinking about D, well, how do I get to D? First thing, thinking about my left, right, I went right. How far did I go right? I went right 2 units. And then I went down 1 unit. So down gave me the negative, and down 1, so -1. But now I just promised you something. So there's good work. We've got good stuff here. But now, when we start thinking about our graphs, start thinking about our situations, well, let's notice something. Let's go back to our original piece of information, our time temp situation, and let's notice that all the values here are positive. Now, this is not perfect, but in any situation we look at, and the truth is that most real live applications, a negative value doesn't make sense. I don't want to say it never makes sense. All we have to do is just think about some sort of like a business situation and think about their revenue. Their profit. How much money do they actually make? That would be a positive value, but not all companies make money. If you lose money, that would be a negative value. So I'm not trying to say you can't have negatives. I'm saying that just that the situations we're looking at, the things we're considering, negatives are not going to happen. So now as we go forward here, I'm sorry folks, just trying to find my page. Here we go. They give us 2 quick terms, but then we want to start making some of these models based off some information we are given. So I'm going to mention this actually, let me just do it really quickly. Domain and range. Quick terms, we want to just be very clear. The idea of domain is if we're looking at all the values that go with the independent variable. Any value that comes up on my x-axis would be a part of my domain. And then the range, well, that refers to all the values that we would get on the y-axis. So again, just going back to that initial chart, all these x's represent my domain, and then all of these y's represent my range. But that's all we need. I actually thought our book would take that a little deeper, but that's it. They wanted to introduce those terms. They don't even do any set notation with that, just so we're familiar with it. Now we can get back to the heart of what we have left to finish here. They asked us to make the graph based off of this table. So when they did that, two things to realize. Sometimes, especially with the idea of time, it makes it a lot easier if we make some sort of adjustment. Instead of just, especially something like time a day, if you're thinking about laying out your x-axis, well, you're starting at 6 a.m., then you hit 12 noon, then you go back to 1 p.m., laying that out as an x feels goofy. So in some of these time situations, whether it's literal time of day, maybe we're looking at a date, so we're thinking about what's the difference between April 1st and May 1st? One thing that's helpful is to start off at time equals 0, and then whatever units you're thinking about, if I start off with 6 a.m. as time 0, then every other time it can be measured in how many hours after my initial time. So time equals 0, then 7 a.m. would be 1 hour after I started the clock, 8 a.m. would be 2 hours, then 3, and so on. That's what they did here. Notice on their axes, they still labeled their y-axis as temperature, and then same thing over here, but their x-axis, it's time, but instead of using time of day, they listed it as time hours after 6 a.m. But now, why do they have two graphs here? Well, a couple of reasons. Number one is just to point out, like we were doing here, that a full graph does represent positive and negative values on both the x and y, or both the independent and dependent axes. So that's initially what they did here. They took these points, again, they made that little conversion so that this was t0, 1, 2, 3, and so on, and then when x or t was 0, y was 50, and that's that point. When x was 1, y is 52, and that is that point. But two things that happened here. Number one is that they realized, again, there were no negatives. So these three quadrants were basically irrelevant. So if we're in that situation, why bother showing this stuff if it has no meaning? Oh, and temp is another good example, by the way. We're looking at positive temperatures, but you can have a negative temperature. We don't see it too often in New York City, but we do occasionally get into negatives. So it's not that this couldn't happen, but it never did. So why draw these if they have no bearing? That's a big thing they did here. They also used a few other little things we talked about before to make my picture better. Initially, they had this scale they were going by 5s for the number of hours and by 20s for the number of degrees. But if we'd like our picture to look better, well, they even could have given each dash represents 1 hour, but now they made it every 2 hours. That's pretty good. And then for temp, they jumped. Instead of starting at 0, they made a jump so we don't have all this empty space. And now they made their temperatures jump by 5 degrees, so that way a minimum temp of 50, a max temp of 73, we could see them all nicely here. Instead of everything being clustered, and if we're trying to identify XY pairs, like this one, this point is supposed to represent this data value, but it's so messy right here. Going down, how many hours after 6 a.m. is that? That's really tough to tell. Is that 2 hours? Is it 3 hours? I can't tell. What is the temp here? Well, it's more than 40. It's less than 60, but it's still really, really rough. But by cleaning up everything, by making my graph better, by showing, using a decent scale, highlighting the real values there instead of allowing all this empty space, now when I look at this third point, now it's so clear. This is 2 hours after 6 a.m., so that would be 8 a.m., and the temp clearly lines up with the 55 degrees. So that's what they did here. They took the information from here and they managed to then plot it. But we realized again, this was fine. This was a correct model, a correct graph, but this one was better. This one allows us to use this better. So we could think about, well, we could see the whole big picture in this day. You know, if we're thinking about New York City, what time of year are we looking at? Kind of like our low temp was 50. We went up to the low mid 70s during the day. We finished at the end of the day around midnight, just above 60. That might represent this time of year. Maybe a little later, maybe a little bit more middle of May, beginning of June. Maybe if you want to think about the fall, the early part of fall, we might be something like this. But for New York City, this would be unlikely on a summer day or unlikely on a winter day. So just having the picture and understanding what it's telling us can give us some information. We can see things like, you know, at what time of day was it 60 degrees? Well, there's 60 degrees. If we look at that, maybe this one isn't perfect, but we've got about 2 points that sort of line up there. This one would be 4 hours after 6 a.m., so that'd be about 10 a.m. This one would be 12 hours after 6 a.m., so that would be 6 p.m. What time of the day, what was the temperature at noon? Well, noon is 6 hours after 6 a.m., so I'd be focusing on this X, which would connect me to this point. And looking at the line here, it looks like it was about 70 degrees, 6 hours after we started, so at noon it would be about 70 degrees. So the point is either two things. If we are given an XY table, we should be able to plot our points. In any of these specific situations, we should make it clear, not just that this is X, that this is Y, to label it with the actual application, to clearly identify the quantities, to include any units. Temp, we know temperature can be measured in Celsius, so we want to be clear that this was in Fahrenheit. And then down here, time can be measured in minutes, hours, days, weeks. Well, here we're clearly specifying hours, not just hours, but hours after 6 a.m. So that's big point number one. Given information, being able to make the correct plot, and then having everything fully labeled. But then secondly, would be able, if you are given something like this, or if you've already made something like this, to be able to use it to answer some basic questions. Now, there is a tiny bit more here. We plotted all the points, but now, completing the model, you don't always do this. They mention the idea of a continuous situation. But again, I'm not trying to trick you here. Once we have our points all figured out, all plotted, what we like to do to make this model complete, not just to leave the points, but to fill in some curve, a best fit curve. So I'm not just literally connecting this like straight line, straight line, straight line. I'm trying to fit a smooth curve that best fits these points. So I'm not just connecting dots, straight line, straight line, straight line. I'm trying to smoothly see that type of situation, and that's what they have represented here. So let's do this together. Let's look at example 3, and let's do one together like that. Example 3 gives us a pressure altitude function. We mentioned this back earlier in example 2. We identified that the altitude is the independent variable and that the pressure you feel depends on how high you are above the ground. So we've established this is our X and this is our Y. So if I am going to make the plot, I'm going to complete the model. So complete the model. That means we are going to, complete the model. We are going to plot the points. That will involve labeling our X and Y axes. That includes any units, any other pertinent information that we would need. Before we plot the points, we'll probably already have to think if there's any scale we should use. And then after we finish all of that, that idea of filling in with a smooth curve. So if I look at this one, I do want to point out they've got all of that set up for us afterwards, and I'm going to ask a few questions just to get a little more practice with that. But I want us to do it together. So you've got your table. Trying so we could see everything all at once. I've got my table. Let me make my plot. Well, there's X and Y. But very quickly, before I even get too busy here, I'm going to notice, oh, wait a second. Everything's positive. So I'm not going to worry about these quadrants. I'm just going to focus here. So I'm already going to start all over. So this is still X and this is still Y. You don't need to write X and Y. Just go back a second. Notice they never labeled X and Y here, but for some people, they always like that reminder. I need to see the actual quantities in units, but if you want to still remind yourself by putting the X and Y, that's fine. So now already establishing X would be my altitude, and that is being measured in feet. My Y is being measured, is measuring the pressure, and that is being measured in mercury. Notice something like this. I don't know if you've ever done something like this in a science class, how your mercury thermometer can measure this pressure. Don't worry about it. You know, this is the inches of mercury. They describe it. You don't even have to worry about actually understanding the whole context. That doesn't stop you from still plotting, from still making the model. You know, it's nice to have a better understanding. That's great. But just as far as following this procedure, you know, any XY pair, we could follow this. It's already giving us. Altitude is my X, that's measured in feet. Pressure is my Y, it's measured in mercury. I guess they should be more clear, inches of mercury. But they're saying in mercury here, so I'll leave it just like that here. Thinking about scale, well, 0, 5,000, 10,000, 20,000, 30,000. I don't want to be making 5,000 dashes. So why don't I make every dash represent 5,000 feet? So I'd start here, that's 0. And I could either, you know, the subtle variations. Count this as 5, 10, 15, 20, 25, 30. And then notice that altitude is measured in thousands of feet, or just keep the thousands. That would be 5,000 feet, 10,000, 15, 20, 25,000, and 30,000. One of the big things, you got to make sure you go out and keep your scale. Some people might say, well, wait a second, why are you doing 15,000? You've got no value. I set my scale. I have to continue my scale to make sure I cover all of my X's. That's what they were talking about with domain. You have to make sure you're showing everything in the domain. So I've got myself covered, but I can't just assign these values. I still have to maintain a scale. So I can't go 10,000 and 20,000. I still have to keep the scale of every 5,000. Looking at pressure, well, I have a low value of 10, a high value of 30. I'm going to have to get up to 30. There's no reason to make a jump here. You know, what is my scale here? Let's stick by 5s. 5, 10, 15, 20, 25, and 30. Our scales do not have to be exactly the same. Just out of curiosity, did the book? Yeah, the book kind of did our thing. They went by 10,000s for feet, so you notice you've got a point halfway in between 0 and 10,000. But they made a similar decision over here. Oh, they were even more clear. They literally said inches of mercury. Okay. Again, they said in mercury here. I wouldn't give you a hard time. But as we said, it's better to be even more clear. Inches of mercury. But everything's still on track. 0, 30. 0, comma 30. 5,000, comma 25, 5,000, comma 25, 10,000, comma 22, 10,000. Okay, I don't have 22, but 25 is up here, 20 is right here. Let me go a little above 20 to try and get 22. Next, I have nothing here. My next value comes out here, 20,000, where I get a value of 16. So this would be 15. Let me just go up a little bit. So 20,000, comma 16. I will just mention, I mentioned you don't need a ruler or anything, but I know some people, they like to have like a little bit of an index card. Even look at that. See how I drew that point? It actually lined up exactly with 15. So maybe I want to adjust that a little bit, just to snake it up just a little bit. But, I'm not busting your chops here. If you've got your point down here, that's a big problem. That's close enough, right? That's part of the idea of having a scale here. We like to be able to get our values as close as possible, but it's still a scale, so as long as we're in the right ballpark, that's fine. Last one, 30,000, comma 10 is out here. So you see we've got all those same points. And now just doing our best fit curve. We're slowly looping down. That's all I'm going to do. I'm just going to slowly loop it down. Hit my points. Subtle things. The book did a little bit of a sense of scale. They did things precisely. We did our work by hand. But it's all fine. That little slope, it's got a little bit of a tilt this direction. All of this looks like it's almost a little bit more of a straight line. But that's all perfect. That is a good full model. How many points do you need? We use however many points we're given. The reality of the situation would be that any modeling situation, the more data you have, the better. But for our purposes, problem number 1, they had 13 data points, so they used all 13. In this problem, we only had these 5 data value points, so we used the 5 data value points. That's it. There's another good example, for you to go through just to get some good practice. But now, one last quick little thing here. Let's just try and use this for a moment. Again, like we said, now that we have the model drawn, we can try and do things like estimate the pressure when the altitude is 15,000 feet. Or vice versa, here I'm trying to give you an X to get you to estimate the Y, or vice versa, I want to make sure this is not an obvious value from the chart. Yeah, this will work. Approximately what altitude gives a pressure of 20 inches. So really just realizing what you're being given. Here, altitude is your X. So you go to X is 15,000. You do your best to approximate the value of this point. And this point, unfortunately, this answers both of them. That's my fault here. But I'll point it out as a separate problem. 15,000. I'd scroll over. Maybe I'd say that's a touch under 20. So maybe I'd estimate the pressure is about 19 inches maybe. So with that in mind, part 2 here, what altitude gives a pressure of 20 inches? Well, I'd go to 20, and now I try and line that up. Okay, it's not quite 15,000. So what is that altitude? Maybe that's about 14,000 feet. So that's the difference here. We're not getting exacts. We would need a full equation to get the exact values here. But by having the graph, by having the model, we can get ballparks. We can approximate. Why would this be useful? Well, a lot of situations. Maybe for a different health concern, you have to realize you can't fly at a certain altitude because the pressure is too much. You need to identify, the pressure, so you work backwards to get the altitude. Maybe it's a forward direction thinking. You're going to be at a high altitude, so you want to prepare for that pressure, so you know the altitude first. So any of these situations, you could find some situation you'd want to know. You'd want to be able to use this, and that it could go either way. By knowing an X, you'd like to approximate the Y, or by knowing a Y, you'd like to try and approximate the X. So Monday, we'll definitely get some practice with this, a little bit more plotting points, go through another one of these. And like I said, we'll get into 9B, we'll extend this. We'll look at one specific type of mathematical modeling that we call linear modeling. Now, it's only one example, but that doesn't mean it's one situation. There's lots of different ways that once you have these points, there's lots of different patterns. So I'll mention a couple of them, but the idea of linear is that my points would all fall on a perfect straight line. So there's lots of situations that are modeled this way, but there's other situations the points get modeled more in like this upside down parabola, or others. There are different mathematical curves that we can see, but like I said, this straight line is the idea of linear. That's the one we're going to get a lot more specific with. Very friendly, a lot of ways to work with this. And, we'll still keep seeing units. We'll see some real life applications, but still, it's just an extension. So make sure you get some good work done with 9A, so that way you are ready to move on. And I should note real quickly, I'll put in the email, this is assignment number 11. This is, the homework is page 524, numbers 9, 11, 15, 23, 25, and 29. We're probably only going to have one more homework after this, so as I keep saying, make sure you've got your 4 submissions. Make sure you're getting all your homework credit. Okay, everybody, let me know if you have any questions, and I'll see everybody on Monday.